Okay, hello everyone. We are back for another episode of investigating multi-computation and multi-computational language design. And the thing that's gotten me excited about this right now is that what we are seeing is the analog of time-like edges, space-like edges, and branch-like edges, and even, in fact, I think rule-like edges in the processes. I think we've got two kinds of concepts. We've got data. We've got sort of an expression which could have lazy parts that have not yet been uncovered. And then we've got the whole process of a computation. It's kind of the analog of nest versus nestless. Nest delivers a result, but potentially that result could be lazy in the sense that some parts of it have not yet been explored. And then there's a second concept, which is the kind of nest list, nest graph type concept, which is the kind of the history of how you got there. And that has a lot of complicated things about, are we there yet? And things about transversals and foliations and so on, about representing what counts as a step in the evolution and so on. All right, that's my preamble. I think Nick had a demo to show.
Yeah,
Nick,
right.
Over to you.
Okay. So here I have a couple of new functions since Tuesday. So first of all, I've been thinking of how to make a lazy versions of any nesting that we have. So the first thing I want to show is like this nest lazy function. It's basically we give it a function that can produce a list or even a lazy list and a list of initial conditions, right? Usually you also produce like in a nest graph, you also produce you give it a number of iterations that you want to go. Here you don't need a number. It's just a lazy data structure.
Why are there two? I mean, I'm sorry, I don't understand why there are two initial values there. Why isn't there just a single initial value?
No, just for generality, it could be just one.
Okay, fine.
Right, but I want to just for generality give it two. So that is going to be a list of trees essentially. Here's the trees formatted as tree rules, right? Because we have a function that converts rules to trees and back, right?
Okay, hold on. Let's get basic framing here. Could you just do with that thing where you say nest lazy? Could you just do a regular nest? Actually, a regular nest list.
It's more nest graphing.
Well, but I want to see nest lists because I'm trying to understand what this. Okay, so that's the pure tree-like version. Right, that nest list that nothing has merged.
Yeah, I guess it should be something like that. If you nest in it and maybe even continue back.
Is that right? I don't think that's right. I think you wanted the thing you showed before. I don't think you want the map in there at all. I think it's literally doing.
Well, it's just in this way you're just showing the branch of.
No, I know, but so in that case, could you make a tree expression out of that or something? Expression tree.
Out of this.
Yeah, out of that nest list.
Hold on, isn't this taking advantage of weird nestability stuff that just happens to work?
Yes.
I mean, shouldn't you be doing nest tree?
Yes, probably. Is there a nest tree? Yes, there is. What is nest tree? Okay, let's take a look at that.
And then it should be a map in there.
I don't understand what's happened here. Actually, look, do the nest tree. Do the nest tree with a single initial condition.
Yeah.
There you
go. Okay, so that is now a ternary tree.
And this is essentially this first one. It's like a strict version of this lazy tree. Here.
Okay, could you just do that nest lazy with a single one as the initial condition? Okay, now
well, what is that second? Oh, sorry, never mind. Yeah,
it was just an empty list, but this wasn't built.
I'm confused here. So you could also have a nest tree lazy. But this thing here, I don't understand the arrows. What are the arrows?
Well, the arrows, well, that's one representation of a tree, right? If you have this kind of arrow, 1 arrow, 2, 3, and I think rules, is it rules tree that can convert it into actual tree, right? If you do it.
Yeah, okay. All right, so just so I understand, so if you can cut off the nest lazy at a certain level and then convert it to a tree, that would be helpful.
Or that's basically what this is doing, but instead of doing it interactively, where you're clicking in order to expand the tree.
Yeah.
Yes, but it's a rules tree.
I think it's just that it's hard to implement this with a tree and
Yeah.
have all this dynamic stuff going on.
No, I understand that. But I'm just saying that the thing you're getting is not the output of nest, it's the output of a nest tree converted to rules format. Is there a tree rules function?
Yes.
Okay, so can you go down to your nest tree that you just made? Yeah, okay. Okay, so that's what this is giving. It's giving the tree rules of that nesting. Okay, I'm now beginning to understand what this is.
But really, it's giving this lazy tree. It's just that it's displaying it in a way that's reminiscent of tree rules.
Isn't it exactly tree rules? No, it isn't. Look at it. It's not exactly.
No, like internally, it's some crazy expression. This is just the boxes. Like this is just a print form.
Okay, fine.
Yeah.
Okay, all right. So now there's some traversal order.
Right.
Okay, so what happens if I want to do a breadth first? If I wanted to take the tree to level 3 to breadth first level 3 or something. Maybe this wasn't the demo you intended to give. I think I understand what this function is. Go ahead.
I was going to go into other direction. So, and then when you have this basically a lazy tree or list of trees, then you can make it some kind of traversal. And I have a very simple one, which is just goes randomly in the direction that it's never visited yet, right?
Mm-hmm.
And searching a particular value.
So try it.
And what it produces basically, it produces a new lazy tree, the same, but it's
which is as far as it had to go to get to 15.
Yes, yeah. It's like also what the nodes it visited and the actual path. And this is the position in the input form of this particular value.
Okay. Right. So in that path, it goes 1, 2, 3, 15. Is that correct? Why isn't 15 in the path?
It's a path like a tree path, not the nodes, but actual how you would move in the tree. It's like it's 1, 2, 3 because it's the first tree. Then you go to the second node. There's
okay, but there's also the payloads of those nodes, which would in this case be 1, 5, 15. Correct? No, 1, 3, 15.
1, 3, 15. If you extract like all the iteratively all the subpaths of the final path.
Okay.
And the exploration, because it was random, it also expanded a bunch of other lazy stuff. And if
which is why that other tree got unrolled as far as it got unrolled.
Yeah, if I unrun, it's going to probably do a different exploration.
Okay.
So that's
what's that?
And that was basically the whole demo. And I also can show that instead of just having a tree, I have also a bunch of other nesting behaviors. Breadth first, it would generate just a linear list of edges. Like if you imagine a graph, that would be an edges that was produced during the breadth first search. And similarly, a depth first search.
Wait. There are two different things here. There's the output form as edges, and then there's the question of which part of the tree you're sampling. So I don't understand that. I see. This is the traversal order, the tree traversal order. Okay, so I've got a question. Let's take the tree from up above Could you take that tree from up above, the complete tree? No, not that one. The one where you'd actually generated the whole thing. No. Further up. Further up. That one there. The full nest tree. That nest tree on line 267. The full nest tree. That actual nest tree. Okay.
Okay. Yeah.
Now what I want to see is the tree traversal order. Go back down, and let's look at the set of. Is there a set of edges? Can I traverse this tree, picking up the edges that I visit in a certain tree traversal order? Ian, that would be for you to answer.
Well, trees don't have edges, so.
Okay, well, Nick has edges there. He has the 1-2 edge. So, okay, fine.
That would
so
be a
then,
tree graph.
well, okay, but what I want to know is, how do you get the thing where Nick has gone from his lazy tree, depth first, that's the visiting order. So I want to see that for an actual tree. You see what I'm saying?
Isn't that just like tree map or something?
I would think so. Isn't it? Why isn't it tree map?
Oh, wait, is it returning? I'm not confused what it's returning. Is it returning a tree or is it returning a list of vertices in a particular order?
When I return edges? Or what?
It's returning the edges of the tree that it went down to get to the place in depth first order.
Okay, yes.
Yeah.
Although sometimes
okay,
it would traverse not following an edge. It'll do something like it'll go, it'll reach the bottom and it'll go back up to the top.
So how is that represented in what Nick has?
Well, we just follow what it's actually doing. Well, if there were actually an end, okay, we can model it with, for example, when we go, I don't know, 15. Otherwise, it's just an empty list. So it's finite, right? This normal would be a finite thing.
Okay. I don't understand this, but the reason that Christopher just said, if you're doing a depth first or even a breadth first, do this depth first. Do a depth first version of this. Yeah, I completely don't understand this because in depth first, there are plenty of moves that you make, which are, scan, what are they called? Vertical retraces, if they were a screen or something, where you're going back. You know what I'm saying? It's not, so these edges are not actual edges on the tree. Is that correct? They're just a representation of the path.
Well, there are actual edges in the tree. I don't understand.
But they're not. They can't be, because you're not. There are places where you go.
Right. To take a concrete example, if you look at that nest tree you have on screen, the one that's already computed, right? If you do it depth first, you go 1, 2, 4, 8, but then you got to go back up to 4 and then to 12. Oh, I guess you do. So if you had to go
that's
from,
actually a top-down depth first. Depth
Say
first
again?
is that's a top-down depth first, by the way. Depth first is usually bottom up.
All right, so you go 8, 4, 2. Okay, so I guess maybe
8, 12, 24, 12. Again, the other 12.
Okay, so Nick, how is Nick representing that?
Well, maybe if he's visiting the same. So, for example, if he's willing to visit vertex 4 many times, which it looks like I think he is, then you can get away with it because you can go 8 to 4, 8, 4 to 12, 12 to 4, 4 to 20, 20 to 4, etc.
Although in nest tree, okay, tree map. Can we see this, Ian? Could you give us the depth first visiting order of the nodes of that nest tree?
Can't you just say tree scan of echo, comma the tree?
Yeah.
But can't you get a list out? How do you get a list out? Ian?
Use tree level.
Okay, so fine. So let's say tree level instead of tree level. Forget the echo.
Yes.
And now say tree traversal order. Wait a minute. What do you have to give in the tree level?
Second argument all.
Yeah, okay.
to level spec.
Okay, depth first.
But that'll give
okay.
the actual trees. You need to say tree data /
Do
at
all
that.
arrow data.
Just data.
Quotes
The
data.
string data.
All right.
Okay. All right. So that's the ordering. So that's what I would expect nest lazy to return. See, well, one thing I'm upset about with Nick's functions here, there's just too much extra wrapping that in the default case is just going to prevent people from using the results. Anyway, what was a general comment? Okay, but okay, so I'm very confused. Nest lazy, I would expect to produce the same result as nest, but lazily so.
It's really nest tree lazy.
It's kind of hard if you have an actual infinite tree, right? The
No, I
only
know,
difference
but
between
it's,
depth first and breadth first is actually how the discovering is going. Whether you go,
I know. I realize that. But I mean,
if it's,
I'm
it's-
saying that the object that you return should be an incomplete. Look, if it's nest, it's the incomplete nest. Okay, what does nest do? You know,
So-
go ahead.
Well, I was just gonna say, I mean, we last time, we had nest list, and then we had sort of the infinite nest list, right? Which returns some infinite list object or something.
Yes.
And I think, I mean, this is the same thing. It's nest tree, or it's nest tree list. Well, no, it's right. It's nest tree is what it is. But then, and it returns some infinite tree object. And so I don't know right now if we're talking about the function nest tree, the infinite nest tree function, or if we're talking about this infinite tree object, or sort of both in some confusing way.
Okay, look, listen. This is the confusion that we had before about data structures versus processes. Okay, I think those are two separate things. There is what is the output, nest, versus how did it get there, as well as the output, that's nest list. Nest tree, nest graph, those are all how did it get there type things that are slightly more sophisticated and more similar to what we're going to do here.
Although I would argue that something like infinite nest list or whatever it's called is not just a how did it get there compared to nest, because it because
it's never going to get anywhere.
Right, because there isn't an infinite nest, because it doesn't make sense. I don't know what your data. I mean, you could have an infinite nest if you could think of a data structure that would be queryable, but I just don't think it makes sense. A confusing thing to say would be to say that fixed point is like infinite nest. But
yeah, that's what I was going to say.
No, but like that's a weird analogy, I think.
I don't know.
Right, because infinite nest list can work in cases where it diverges, but fixed point can only and quote unquote infinite nest only works if it converges.
Look, I agree. Infinite nest makes no sense for a non-halting computation.
For non-converging computation. I mean, fixed point, you give it an infinite loop. It's not halting. It's just it converges.
Yes,
which is why I say it's a different concept, really. I mean, it's yeah.
Well, okay, I claim we are used to single-way computation. It is a little less obvious to me what infinite nest means in the case of a multi-way computation, and I think it might mean something, even when I reserve judgment on whether it could mean something.
Well, the question is, how do you represent the output of a multi-way computation anyway? I mean, now we would do something like a list or maybe a tree.
Or a multi. And that's what multi is. Multi is but
multi doesn't represent the result. Multi represents sort of the object. You then call something like normal or something. You do some query to multi to sort of
I'm going to make a claim. I'm going to make a claim that there are actually two objects we need. We need multi, and we need some kind of computation object that represents the history. Okay, and multi, I claim, is like the analog of a quantum superposition. It is a slice across these trees, across potentially a multi-way tree. That it's a slice across the tree that represents the a particular transversal of this tree. Am I making sense? And okay, so I'm going to give an example where I don't think it's hopeless. Let's take one of these combinators where in the multi-way graph, in the multi-way graph, there is a terminating path in the multi-way graph, and it terminates on something definite and confluent and so on. And there are lost in the woods paths that go off and don't terminate. Okay, and I can imagine something where we could have, and it could be a very useful thing, we could have a function that gives you the terminating part and tells you there are other non-terminating parts or other parts where it doesn't know if it terminates. See what I'm saying? People understand what I was saying?
So I mean, so it basically runs something like this lazy nest tree, and then it returns sort of all of the leaves that were finished, and then, you know, kind of maybe tells you about all the quote unquote leaves that still have stuff below them, but which
right.
hasn't computed yet.
Look, I claim it's a multi where some parts of the multi are unfinished. Some parts of the multi are like black holes, they're done. Time has stopped. And some parts of the multi are still alive and kicking. Does that make sense? Nick, do you understand what I'm saying?
Well, how is it different from this thing, for example? There's some black holes that are finished.
Yeah, I'm just saying the data structure has got to not be some weird, newly constructed thing. It's got to be something where if you said, okay, maybe I'm just objecting to the print form of this data structure. I'm just saying the thing is a multi where some part of the multi is a black hole that's finished and some part is still alive and well. And you can keep going with it. So you could say, run this multi another few steps. You know, and the multi would not contain necessarily, the multi would contain its state, but it would not necessarily contain information about how to keep running it. Did you see what I'm saying? Whereas the computation object will keep information about how to keep running it.
Well, this kind of contains all the information. Maybe you
no, but it contains too much
a bunch of other.
Why? It contains too much information.
Basically, only this function that we provided it, and how to go like forward. It's not too much. It's almost like the minimal data that it's possible to describe all the future results of applying this function to all its children. I don't know.
Going back to Stephen's comment on computation versus visualization, I was thinking, what's the relation with Ian's tree outline, in which you have openers and you keep clicking on the thing you want to open?
Yeah, that's just another nice formatting that can be done for this object, because it's essentially also a tree. So if I had a similar thing, right?
I guess my point is that this idea of clicking and getting more and more information progressively is not necessarily related to something infinite. So perhaps there is a way of combining both things into separating the actual data structure from the visualization part.
Sorry, I
mean, so do you sort of mean though that I mean, surely, I mean, it totally makes sense that if you had something like this multi, nest lazy thing that Nick has, visualizing it in a way like this tree outline, I think would be fantastic. But it seems like the underlying, I mean, at least the top level tree outline function, make certain assumption, you're giving it a tree object that works in a certain way, right? And it doesn't have any rules about, well, if you click on this triangle, it might have to recompute this whole tree or something.
Although that is something that we want. So John Fultz had a proposal for something called tree view, And that would be useful for things like a file browser. Like right now in the prototype build, there's file system tree, but that requires you to gulp kind of like an entire directory and all of its subdirectories into memory before you can create the outline. But you would like to be able to produce outlines that are basically a lazy nest tree. So you click on an opener and only then do you read what files are in that directory.
Well, so that's probably almost exactly the, the thing that Nick is demoing here, right? And I guess it's sort of a pure visualization object in that case. I'm guessing, but yeah.
I mean, we need lazy nest tree for the visualization. We need it for like streaming transformations.
I see.
What's the streaming transformation?
Well, so for example, like doing an XML to JSON transformation without needing to first build an entire tree in memory.
Yep.
And then just converting as you go.
So that's interesting, and that's not unrelated to Leonid's chunking business.
Right.
Yep, precisely.
Okay, so let's review this again. So what we're saying is, okay, I'm sorry. I want to go through this again. This concept of the multi, which is the essentially quantum state. Is that making sense to people? It's the slice. It's what you get at a particular quotes time, whatever that means, whatever that transverse thing that you're looking at is, and that is distinct from the computation object that represents the whole history. Is that making sense to people?
So the multi-object fundamentally represents a set of different possible positions. Okay. Not a tree, not a thing that tells you here's what choices I made necessarily. It's just, it fundamentally represents a set. You might be able to query it in other ways, but that's what it represents.
Right. And that set. Okay. The point is that set, I don't think you can even deduce the branch hill graph from it because you don't know anything about its history. But one thing that is true is, given a multi, you can always keep going with the same time evolution that got you to that multi. You can keep going on the multi, applying the time evolution operator again. Does that make sense to people?
Doesn't that just mean you keep computing with the same foliation that you had that yielded that particular slice?
Yes, for example.
Yes.
Well, I don't know. It's the same foliation. I mean, you keep going. That's a slice. That's a transversal. Now you keep going, applying the time evolution operator, and it's up to you how thick you want the different parts of that time evolution operator to be. You'll get another transversal. But the point is, just like this is a faux initial condition, if you understand what I'm saying. The multi is something usable as an initial condition. Does that make sense to you?
Well, because you don't have the history.
It's more than just a set of events, because event basically holds both its input and output.
No, I'm not talking about events. I'm talking about the states. I'm talking about the states. I'm talking about just the states. What's that?
Well, you have to at least store the actual history one step behind it.
Why? Why?
Well, branch hill graph, for example.
I know. I'm saying you can't derive the branch hill graph from the multi.
Well, if it's a set of
events,
then you can.
What?
If it's a set of events, then you can.
Okay, fine. But I'm saying there is a concept of the thing that lives in a slice. Possibly we can thicken the slice, but the whole point is we're not storing the whole computation history. It's just like Nest. It's just a result. Does that make sense? And we can keep going, applying the time evolution operator to that thing, right, to get another just the result thing. Does that make sense? I mean, it's like saying with nest graph, okay, nest graph is a history, but in nest graph, you could look at the outer boundary of nest graph. That's more like the thing that we're imagining this multi is.
But Stephen, why do you want the history to be discarded? Is it just for purposes of simplicity?
Yes, I want to make sure we understand this is the current structure of space, for example. This is a current hypergraph. This is a bunch of hyperedges. And it's the current, it's the notion of the world as it is now.
It's just a branch-like hypersurface, but you don't have anything that came before it.
That's
and so that,
correct,
and as you're saying, that could serve as an arbitrary initial condition because it's basically ahistorical. So you could just start history from there if you wanted to.
Yes.
Okay.
But I'm just trying to clarify what it is, because it's like nest list, right? You can go nest, and you get to a result. Then you feed that into nest list. You can store history for a while. Then you get the result of that. You can consider that the result, and then you can store history and so on. I'm just trying to break up the different concepts here so that we have the most important things. The thing I'm not liking about the things that I'm seeing here is, Nick has a giant Swiss Army knife of, things that are being returned by these functions. And I'm saying, I don't think that's what we want. I think we want a function, there can be a function that returns the Swiss Army knife, so to speak. Okay. But we want functions that are much simpler, that just return, like we could have said, okay, every function that we have that returns kind of diverse outputs. Like, let me give you an example. Find shortest tour. It's super annoying that it returns the length of the tour and then the list of tour, visits. Okay. Every single time I use it, I'm annoyed by the fact that I have to say first, last, whatever, right? I would have been much happier. Now, in that case, I don't know what the right way to do that one is. And maybe that one in modern times, we should give it another argument, a note to be made for LCC probably about that allows you to select one of those two things. And the default probably should have been a, see, look at that. See that? See that?
Yeah, it would be an association or something. And then, right.
It should be an association.
About your general point though, but I think I agree, functions should be kind of fairly minimal a lot of the time, but the objects should be pretty, are often pretty Swiss Army knifed, right? Yes,
that's right. That's what I think. And my point here is, I think there is an object, there is a function thing like, I think multi is a new concept, like a list, like a set, like a whatever, that is useful, that is very minimalist. And a computation object has lots of hair in it. Go ahead.
But see, now, one thing is though that, well, right. It blurs a little bit when you have stuff like graph, where a graph is fundamentally, that's the Swiss Army knife data structure, but it also is kind of a function, right? Because it has several constructors and you can give it lots of complicated options and so on. So there are some cases where it's a little bit unclear.
Fair enough, fair point. Okay, but the thing I'm trying to understand here is, okay, we're trying to. Okay, Nick, what are you showing here?
The multi-object that I have already. Which is, well, maybe it's not minimalistic as you want, but it contains some rules that how it can progress to a new multi-object.
Okay.
Right?
Okay, but let's just zoom out for a second to the overall picture. The overall picture is, we have, I'm still a little bit confused by the relationship of laziness to all this other stuff. Okay, because we've got laziness and multiness. What is the relationship? Or are they orthogonal concepts?
I think it's just that multiness, some of the things you'd like to return from some of these multi-way functions are things like the multi-way system, as a tree, but fundamentally it is often an infinite tree. And so that's why, or it's at least a very big tree. And that's why, we're talking about lazy stuff as a natural way of representing it.
Okay, all right. So then we've got three different concepts that we're dealing with here. Okay, we've got lazy, we've got multi, and we've got computation object. I think. Am I making sense?
Yeah, well, okay, yeah. Computation object would be the thing that we wrap, for example, where is that find thing? So, like, for example, this is a computation on the multi-way data structure.
Yeah, that's right. That's exactly on the computation object data structure. Or multi-computation. It could be called multi-computation object, whatever it is. I would favor just having it be a computation object. And that computation object is the raw material on which tracegraph, for example, can operate. In other words, the computation object would store enough to be able to extract from it something like a tracegraph. Does that make sense?
Sure, basically, like here, this is the history. So you can trace the underlying multi-way again.
Well, this is yet a different thing. No, this is no, because what I'm saying is, just like trace in its rather, inadequate way, is a complete representation of a computation. Right? That's what we want computation object to be. That has nothing to do with the path. The path, I don't want any of this crud in the path. I just want the frigging path. If I say find me the path, I want to see the path. I don't want to see any other extra crud. I just want to see the path. Right?
Yeah.
And because that's what a function called find path finds the path to, and in that case it would probably be, we might even apply find path. I don't know whether it would make sense to say find path of the computation object from A to B. I don't know whether that's actually find path or whether that's something different. Does that make sense? Right, but none of this extra crud is relevant. Right? If it's find path, it's finding a path, and that's all it's doing.
Okay.
Right?
So it could just return a path.
Yeah,
right?
That's what we want. Just a path, nothing else. Right? If we want to find something else, then we should ask for something else. Right? Because it's really important that we not have functions that return a bunch of extra crud. It will just be unusable. It will just mean that you have to, that's one of the things, for all of its problems, the current design of multi-way graph or multi-way system in the function repository, it does actually return fairly clean things, and that's good. And it doesn't return, a giant sort of, a Swiss Army knife or whatever, from which you then have to extract something and extract something and extract something. You see what I'm saying? And I think that's a really good feature.
Path can be a default, but you can agree that sometimes the other things are also useful.
Sure, that's fine. But I don't think it should come out from a thing called find path. I mean, maybe it has an extra argument that gives some other things. I don't know. But yes, those things should be findable. But I'm saying not, it's very important that there's a very clean version of what comes out for these things. So it's actually usable by people, right? And so they don't have to understand. One of the problems we're going to run into, okay? We've had many meetings about multi-computation and so on, okay? This subject is not simple, right? And if you look at the, this is on the higher end of conceptual difficulty, of things that and so therefore anytime you throw people this giant pile of stuff with lazy structures and this and that and the other, they're just going to drown. They're going to give up. Same thing that we found with breadth first search right now. If you go to the breadth first search page, nobody's using it because it's too complicated.
Scan.
Yeah, breadth first scan. Right. We can't see that window, but if you're clicking on
just
window,
thinking.
So, okay. Right. I mean, nobody's using this. It's too complicated, right? We got to factor this in such a way that it actually provides, you see what I'm saying? This is not a good thing this is not a good design. Right. So, I mean, again, this is our challenge, is to factor this functionality so that people can actually use it. And so the conceptual model is, okay, so let's review what the conceptual model is. Again, do you want me to share or do you have more stuff to share?
No, that's it.
Okay.
You can share.
Oh, Christ. Okay, so no, wait a minute. I had a you said I had notes from before. Okay, let's I'm going to make another set of notes because I think apparently. Okay, let's factor again. I mean, we seem to be looping around the same things over and over again, which is kind of frustrating. I mean, okay. All right, so let's make another set of notes here. Where am I putting these?
Put it in SW notes.
Has anybody looked at these SW notes that are here? Have you been reviewing these? Are these relevant to what we're talking about right now? By the time we're at version 26, we need to go through and inventory what's there, try and pick out and summarize what we've already got.
I mean,
I'll do that.
we had done that at some point, right? We looked at all the notes from these multi-computation language design meetings, and we did try and summarize from that, and we did build a
where is the
roadmap from
summary?
that.
So I claim there are three basic things. There's lazy data structures. There's multiness, and there's computation objects. And there's and basically there's functions on computation objects. Okay, so another thing that was added is something a little bit different from this, which is the thing that we were talking about subsets, for example. Okay, which I claim is a little bit different. That's more like, well, I don't know. Is that different? I mean, it's like lazy iteration functions or something. Am I making sense?
Right, yeah. We can make
Okay, so
a bunch of objects like that.
Okay, so let's look at what is a lazy data structure. What is a typical example of a lazy data structure? It's like range of infinity. Now, maybe this lazy iteration functions is the same deal, that it's like subsets of range of 20 or something, right? That
It's kind of
is
the same data structure. It's list. It's just different generators for a lazy list.
Right. Yes, these are not data structures. These are functions you're talking about. These are constructors for a single object.
Okay, this is constructors for lazy objects.
Well, specifically lazy list.
Okay.
I mean, I'm not sure that's the name we're going with, but in this case, it's lazy list. I think it's important, though, I mean, we're just talking about functions versus data structures. So I think,
Yeah, okay. So, I mean, this is potentially a lazy of range or whatever. Let's say something like this, right? And then we have to have, that's the constructor, but now we have operations on lazy lists. So one of the things that is still different for a lazy list, well, it depends how it's cached. I mean, we could do something which just says, how do you index this next object thing, right? You've got a lazy list, and it is very car-colorish. Are there cursors on the lazy list? You see what I'm saying? So in other words, is there a notion of like a stream, as there is in a stream?
Well, that would be another data structure, not a list, I think. It's like list, by definition, I think it's a data structure that lazy list that have just a first and next or rest, basically.
Okay, all right,
No.
fine.
Well,
So then
that's,
maybe
I
there's a-
mean, that's one model. I mean, I'm not sure exactly what the interface should be. I doubt it should involve cursors, though. I mean, here's one of the big things. I mean, this is one of the things I think was useful from being a summer school project, for example, was the fact that there are lots of different data structures you can imagine having. Like, oh, I'm going to have this data structure. It's sort of like a, I have a lazy list, then you might have a lazy tree, then you might have a lazy DAG, then you might have a, whatever. The problem is a lot of those objects, or I have a lazy list with a cursor in it, whatever, right? A lot of those objects don't have existing, they have no analogy to eager data structures, where those eager data structures have functions, right? And so you'd have to invent a whole new sort of set of functions to interact with them.
exactly.
And I think it's much more useful if you basically say, this is a lazy data structure that is entirely analogous to a list. Its semantics are exactly that as a list, but it's lazy. Then you get to inherit all the list functions. So, for example, lists don't have cursors, so I'd argue, you shouldn't have cursors either. At least not visibly.
Right. I mean, we could, by the way, have a data structure that is a list with a cursor in the data structure collection.
I don't know what that would be. How is that not just a list and a number next to it somewhere else?
Pretty much what it is. Yeah, it's pretty much what it is. It just stores it, but it stores it.
But then
like
what are the
stream.
operations?
Hold on. Like a stream, it does the same thing that a stream does. It has a seek. It's a stream-like list because a stream knows the stream pointer. See what I'm saying?
Sure. I guess. I mean, if there's a set of operations that could be useful on it, then sure, I guess you could have it.
Right. I think we should look at that. I think it's the analog of a stream, but for an in-memory object. I mean, that's exactly what years ago. What the heck are those things called? We have oh my gosh, what is it called? In the stream system, there is a what is it called? Somebody must know this. Don't tell me the functionality is that useless. You can get an in-memory stream. What is it called? This is pathetic documentation. Oh, string to stream. That's right. String to stream. Do you see what I'm saying?
Yeah, sure. I just think streams have not really been a super winning concept.
Successful.
I mean, they've only really happened, when you're doing really low-level I/O stuff.
I understand that, but string to stream was an attempt to make a cursor-based. It seems to me this will be a good thing to have in a data structure collection, a string to stream data, a string stream.
List to, yeah.
Yeah, right. Could also have list stream. So it will be, these will be two, I like this. I think that there could, two data structures.
Well, but in this context of lazy, it would be just lazy of list. It would be a lazy version.
No, it wouldn't be. No, it wouldn't be, Roman. No, it wouldn't be. No, that's the whole point. That's what we keep on saying. The whole point is, if we say a lazy list is just like a list, it doesn't have a current element pointer.
Right. I mean, this is a separate discussion that we're talking about right now. So from lazy lists, I mean, we're just talking generally about whether it would be nice to have some sort of basically streams for lists, which
exactly.
I'm skeptical.
What Roman is saying
useful,
is making the mistake of saying that that's what a lazy list is, because it isn't. That's not what a lazy list is.
A lazy version of a normal list.
Yes,
right.
But then that's not
thing,
this.
Though, but yeah.
That's not this. This is something which contains a stream pointer, right? A list does not contain a current position pointer. You see what I'm saying?
Right.
I wanted to show this inactive example because I think this is not what I would call lazy. This is some sort of symbolic list in which we can have length n, and then we can do some operations. But I wouldn't call this lazy for the same reason you are saying. This has an iterator, a pointer, a current pointer.
What has a current? This doesn't. Wait a second. A lazy list is not a list with a pointer. Or do we disagree about that? That's not what a lazy list is. A lazy list is just something where not everything has been evaluated. That's my point of view. And I think I think it's the correct model for us to provide to people. And in other words, it's a list where were you to ask for the millionth element, it would just give it to you. And, assuming it could. And if you were to ask for the millionth element again, it would behind the scenes have cached that list because it knows that it doesn't have to recompute that.
These are sort of implementation details.
Probably very close to what Leonid's streams are, because they are kind of caching lazy lists with exactly this.
It's
behavior.
It's got stream pointers again.
Mm.
I'm not sure. These are different
understanding.
terms. I mean, I think.
Well, maybe
there is no stream pointer in a thing we call a list. There's no pointer in a thing we call a list. It just has indices, but it does not have a current index pointer. Am I making sense? There is no notion of a current index. I've got a list here.
But I'm not sure there's much disagreement about this. I mean, I think we all kind of agree on that. I mean, it's just right. I mean, there's other semantic things that has to be the same too. Like, for example, it has to be immutable, right? You can't have immutable lists generally are not immutable, for instance.
Well, okay. So, behind the scenes, this would be mutable. A lazy list would behind the scenes be mutable.
For the purposes of caching, it might be invisibly mutable, right?
That's what I mean.
That's irrelevant. We're just talking about the visible semantics.
Yep. Okay, so let's see if we agree. Okay, the concept is that a lazy list is something that can be symbolically described by something like this, potentially. And that would return, I mean, these names are no good, but that would return a lazy list, which is a somewhat opaque thing, okay? Were we to say normal of that lazy list, if it were finite, it would just return the list. Am I making sense? Within that lazy list, if we ask for element 1, 2, 3, 4, 5, it will be able to generate those elements, but there is no notion of the current element. Do we agree about this?
Yes, I mean, that's
you
much a consequence of immutability. I mean, the other thing would be iterators, which are mutable, which is something different.
Well, what do you mean by that? You mean a thing with a pointer, yes?
Yeah, I mean, an iterator is a mutable object that produces elements of something one at a time, but you cannot go back, and so it changes its internal state every time. So they are very useful, for example, for combinatorial generators, where instead of generating a whole large set of, say, trees or so, you only look at one of them.
Okay, that's a different concept. Okay.
Yes.
So this thing here would be a function which gives us, it's basically it's something not very familiar in our, it's a next element function. It's a next element thing that could take a list inside it, and it will always, every time, well, the heck, in our language,
it's a little bit like it's a little bit like take drop, but really it's first rest for a function.
Except it isn't, because it's mutable.
No, I know. I'm saying I mean the immutable version will be something like first rest. You can get a similar effect.
I understand, but so it's something like, as appends to a list an element. Okay, this would be
I mean, right now, basically the only mutability that we have is either in the data structures framework, which is a different thing, or in the symbol table. And this is not in the symbol table. So I think this would be a new kind of mutability that we don't have right now.
Well, it could be in the symbol table, because we could say
internally there can be some symbol hiding somewhere inside.
No, I don't think it needs to hide. I think it could just be.
If you have symbolic expression and you call a replace add, would it be just generated a new version? It's immutable, the whole list, not
Yeah.
just the part of it, right?
Yeah.
What if we have some mutable version of replace add for expressions in general?
Well, remember, the only way, as Christopher was pointing out, the only way we can do mutability is to anchor it on the symbol table. Actually, we have that thing that I don't think, has this ever been, what is that thing called? The thing that allows you to have a mutable, what is that called? We had this notion of an expression object, did we not? Did we ever introduce that in the end?
You
And
talking about
remember
expression?
No. Much longer ago, this concept of a mutable anonymous object, right? Like a symbol, but it isn't a symbol. It's a construct that you can make with a UUID.
So
You know what I'm
there's
saying?
something a little bit like that. I think there's a compiler data structure called value that you can use to do similar things. So you can have a value data structure, you can set it and you can get it, and it effectively does that.
No, the thing that I'm talking about is a thing
Persistent
called
object,
expression
maybe?
object. What's that?
Are you thinking of persistent?
No, I'm
object?
not. No, I'm not. I'm not. Roman, do you know what I'm talking about?
No, the only thing that came to my mind is that compiler thing.
Okay, what we had, and I don't know what, I mean, I can go do a search for this. We had this notion, I think it was called expression object, okay? And what it is, it's an anonymous symbol. Do you understand what I'm saying? Okay, it's just an expression object with a UUID that is assignable to. Does that make sense? No. Do you understand what I'm saying? It's a thing. Oh gosh.
I think it sounds like it's identical to this data structure and everything
Probably
with
is.
API.
It probably is. Yeah. I mean, this was a much earlier thought, and I don't think we ever came back to it. Let's see if I can do a search here. Let's see. Okay, 2017, 2018, 2019. Mutable object was the proposed name. It was an SW Notes expression object. Look at that. There it is. Oh, gosh. 2018. Okay, create mutable object, delete object, etc.
This looks, I mean, even the API of this thing looks
very
like
much like the
data
compiler.
structures. And I noticed that one of the notes had TWJ in its title. So I'm guessing this turned into the data structures.
Yeah, and I think we never came back to this particular idea.
But I think it exists. Okay, yes, okay, right. In the compiler, there's this create reference thing, which is almost certainly, you know, where the, okay, this I think was done, but it's just called the value data structure. If you just go to the documentation, it is exactly what you're talking about.
Okay. I think it needs to be better exposed then.
I'm not sure about that because I think it's not, I think it's a non-idiomatic way to program. I mean, there's some cases where it's, you know, where it can be convenient for stuff like caching, especially, but I generally think it's, you know.
Look at that. It's the very, very first thing on the data structures page.
Yes, yes. I think people reach for this sort of thing a bit too readily because it's something that you use a lot in other more mutable programming languages, but which, you know, I don't think we should make too easy to use.
Okay, well, I think you're right that this is the thing. Okay, so that would be where the iterator object would live, something like this, right?
I mean, all the data structures, by the way, are mutable like that. Or actually, sorry, almost all of them are. So,
but maybe we should have an iterator data structure to take care of this thing that we're talking about right now.
I mean, there isn't just one iterator. I mean, but I'm fairly advanced in my design for an iterator system, and we'll hear more about it at the conference in the fall.
Well, what's the idea for how it would interact with anything we're talking about here?
Well, it is kind of, I mean, a little bit orthogonal because of the mutability, because every time you ask for the next element, I mean, you consume it. And so it's really, as the name implies, the idea is to iterate over it, for example, to iterate over all trees and test each one of them for certain properties.
Yeah, but as many people have been saying here, that's not a particularly natural thing in our language.
Yeah, but it can be, for example, it could have.
I know you can graft it on, but it's not obvious you want to.
Well, but if you don't have it, then you either need to have a loop where you always call a function to create the next element.
Look.
Or
No, you don't. If you have a scan over this, for example, you're throwing away each element as you get to it, but you're successively visiting elements.
Yes, I mean you can do the same things, but one advantage of mutable data structures is the compiler interface.
Yeah, but we don't. But mutable data structures are really alien to our language setup. So I think we should try to avoid them. But I think that you can get, like, if we've got this, and for example, let's imagine we do a scan of an if blah blah blah, of a so, whatever it is, right, onto lazy of subsets. That would allow us to visit.
Select, right?
But it depends what you're doing on it.
No, if you use so, then you reap them, then it's just select.
No, it depends what you're doing. Well, whatever, you can do that. Okay. You might want to make a decision. I see. The problem is, what if you make a decision about whether to go on based on what you got back? That's a scan while type idea, right?
Yes.
Which we don't have.
Or we just use a while loop with an exit condition. Or
yeah, right. Okay, fine. But okay, let's come back to where we're really trying to get to here. Okay, so we've got this notion. So this is not clear whether we're doing this right now. This isn't although the thing that we definitely do want. Okay, in this case, we want to be able to scan over that, and that might require our own sort of special code for being able to do, so if this was more complicated than just lazy subsets, if this was a more complicated expression that we had made lazy and that is in fact a very long list, we might want to be able to scan over it with, in some lazy way. But the basic point here, right, where it is getting an element on demand. Does this make sense to people? That the thing outside of this, the question is, one thing one could do is everything's lazy until there's an explicit release, an explicit kick to stop being lazy, an explicit wake up. Do you understand what I'm saying?
Well, every time it goes for evaluator, it's an explicit wake up.
No, but that's not obviously the correct thing. I mean, it could be the case that I say this sub 1 million, okay? And that could be that the lazy just eats that and the whole thing is then lazy. And that it requires something that says wake up to actually evaluate it. Like hold and release hold. You see what I'm saying?
But why would you do that in the first place?
Do what?
Well, provide that 10 to the 6, but say, oh, don't do it. If you don't need it, then just do it when you need it. I mean,
Fair enough. Okay, so then let's loop back around. Okay. There are potentially many functions that could be made lazy, as in don't do it and don't actually evaluate the function until you need the result. Right? So implementationally, we would have essentially a table of lazy versions of these things where this would have some kind of generalized up values that says if you need the nth element, we might have a special algorithm to get you the nth element. Does that make sense?
Yes,
If
I
it's
mean
not
that
a list,
is.
yeah.
I mean the idea is to say, okay, we have these lazy lists. So now let's look at all functions that take a long list as argument and work in such a way that
No, we don't have a lazy list yet. We don't. Look at this actual thing. It is not a lazy list. It is a lazy variant of this function. Okay, so is it the case that
the result of this expression is a lazy list of subsets?
Okay, all right, fine. So the one thing we have that we feed to other functions is the lazy list. We have generators for the lazy list, which are lazy variants of ordinary functions. Am I making sense?
Yeah, I mean, all the functions that produce lists are candidates for lazy versions that produce lazy lists, right? Range, constant array, nest list are probably the most important ones. Table,
well, okay, but the same thing will be true of so do we want a lazy tree as well?
Sure.
I think so.
And
Actually,
in case of
let's
list,
take a look at lazy constructs.
The combinatorial generators are an important class, right?
No, they're generators. They're generators. They're part of this story here.
Yes.
Lazy constructs. We've got lazy list. We can imagine. Whoops, I typed lazy string, but I meant lazy list. But we also have the concept of lazy string. Will be another one, where the most likely source of a lazy string would be a file. Making sense?
Yes, but I mean more generally, if the lazy read list would be the closest analog, because that's
lazy what?
Lazy read list.
No, that's not what this is. No, these are constructs. These are constructs.
Okay,
right?
okay, yes.
Okay,
sorry,
so lazy
yes,
read list. You see, these are constructs.
That goes
up
to
in
constructors.
That's a constructor.
Yes. Okay.
Right? This has this, for example, might have a constructor of lazy read list.
Yes.
Okay, now what other things will be our lazy constructs? We'd also have lazy graph, presumably.
Well, the problem with lazy, well, maybe you could have lazy graph. I mean, the hard thing is that it's sort of, in these other cases, we have we've sort of picked a frontier. I mean, for example, with lazy list, maybe we could have a lazy list that's lazy, it starts at the end and goes to the beginning,
well,
right? But we've arbitrarily chosen that that's a little goofy.
Two-dimensional, e.g., 1D lists are straightforward. What about
they're
a
not.
2D?
They're not. You think they're straightforward, but they're not. We've arbitrarily chosen that the first part of the list will be concrete and that the arbitrary part will be on the right. It could be on the left.
Yeah, I agree. But I don't think I think it's reasonable. But imagine a 2D list where there's a more complicated region that is filled in versus not filled in.
Right. In practice, at least with the current, I mean, we've talked about having other kinds of infinite arrays, but at least with this lazy list thing, I think if you had a 2D one, it would just be, from the top left kind of thing.
Yeah, okay, fine. But that's a non-trivial decision.
It's a exactly. So,
list?
Sorry?
What is a 2D list?
A lazy list of lazy lists.
I see.
But I mean, we could imagine having another data structure for generic lazy arrays, but that's another, let's not get into that right now, because that's a complicated question. But for graphs, sorry, go ahead.
I was going to say that with inactive of table, we can nest them, and then we can do I goes to N and J goes from I to something else. So we can have ragged arrays and things like that. Now D understands those things already.
Right. I mean, I think that's a different like the reason why I'm saying, we shouldn't talk too much about lazy arrays is because I think that if we had, I think that a lot of the applications of lazy arrays are pretty different. Like, I mean, with that table thing, it's very natural to basically make something where you have a generator function where you give it a position and it returns you the element, which is useful for all sorts of things. But it's fundamentally very different from how a lot of these other lazy operators we're talking about work. I mean, for example, that you could do random access much more efficiently and so on. But sorry, I mean, I was just bringing this up though to say that lazy graph, I think it's not clear how it grows. I mean, it's not clear where the concrete part is and how it grows outward. And there are things about, yeah, I think it's, yeah.
Sorry, which one? Lazy graph. Yeah.
Lazy graph, yes.
Yeah, that's non-trivial. That's what we've been talking about foliations and all that kind of thing. I agree.
Well, no, but lazy trees, I think, are well defined. But there's an obvious.
They're not well defined.
Lazy
graphs, they've got a tree traversal order. They've got a tree traversal order issue.
No, but it's obvious how the functions. It's obvious where the concrete part is and where the lazy kind of cutoff bits would go. Right, we're doing it so that the root is concrete and that the leaves can be lazy.
Wait, did we forget to invite Brad to this meeting?
I can ping him right now.
We forgot. How did we do that?
Okay, but I think that trees, it's clear where the concrete part is. That's not the case with graphs.
It is for DAGs. It's a little clearer.
Sure. But we don't have a DAG data structure.
I know that. I know that. If a
graph, we should invent a concrete DAG data structure and make a whole library of functions for it before we should make a lazy one.
I think we're going to need a lazy graph because I think it's deeply related to computation objects. That's the problem.
I mean, I'm just trying to imagine, I'm trying to think of functions that operate on graphs. So if you had an infinite graph object, let's say it starts at a vertex and it kind of grows outward in every direction. And it's guaranteed that there won't be, there are all sorts of crazy situations graph. You can get.
Grid graph.
Sure, fine. It doesn't matter what the graph looks like. I mean, it's just any graph, right? You start at a vertex and you grow outward, or you start at some seeds or something.
Yeah.
So first of all, I think you have to make assumptions about, for instance, hoping that, I'm not going to follow a path and it's going to lead me back to where I started. Because, like, for example, you're allowed to have loops, but you don't want to have a loop where you think, that my degree is 4, but then some later vertex is actually going to connect back and actually my degree is 5.
Yeah, I understand. I agree.
Right? But then the question is, okay, even if you have constraints like that, what is vertex list going to return? You want it to return some infinite list, but it's like, or vertex degree or something. Like, I just think these are like.
I understand vertex degree, because the generator, the nest graph, might not have merged yet. You might have the wrong answer, right? Okay, so let's take an example of nest graph of my favorite example. The x goes to, 2x, x plus 1. And let's start that off from 1 and go 3 steps. Actually, let's go 2 steps. See, it looks like a tree. That looks like a tree.
Sure. I mean, you've done a particularly easy case. You should add, x minus 4 or something like that, or x minus 3, in order to make it more.
Well, even that case, worse. It's joined up there.
Okay, no, but this is a DAG. It's not a tree, not a graph. And you have to go further. The point being that this has edges that, where it merges after many steps, if that makes sense.
Yep. No, I agree.
But I mean, I'm just thinking, I think, right. There might be some kind of infinite graph thing we can have, but I think it's not clear how any of its operations will work. And it's not obvious. I think there are different choices we could make about.
All right, let's not chase this particular one. I think we're going to need it, but let's not chase it right now. In terms of lazy constructs here, I really would like to find an alternative to the lazy word. But in any case,
Procrastinating.
the
Dormant. Dormant is too much.
Yeah,
It's too much.
it's it's undone basically. But we've got all these different things, inactive, et cetera, et cetera, et cetera. We've got, okay, so we've got, here's a question of name for lazy. Because what we've got right now is we've got hold, we've got inactive, we've got deferred. What other things do we have?
Implicit would be something.
No. Roman, what I'm listing here is the things we
Yes.
already have.
Okay,
The concepts
but
we
I'm
already
just
have.
thinking about the possible name for lazy.
And implicit is not going to cut it because we've got too many mathematical implicit things.
We have
But what else
delayed
do we
too.
already have? What's that?
Delayed.
Delay.
We already have implicit region.
Yeah, we have implicit is not going to work. So what else do we have? What other concepts do we have? Holds evaluation for a release. Inactive changes the data structure. Hold is just a wrapper.
Inactive implies you're going to activate it, though.
Yeah, it's a pure wrapper. I'm just listing what we have so we know what are the differences to what we're talking about. Inactive changes the innards of the data structure.
Actually, that's inactivate.
Yeah, inactive is just a wrapper.
Yeah, it's just a wrapper. But it's so what we've got here is, again, it's a lazy is a wrapper much like inactive, right?
Well, you can also say that it's like a hold also. It's like a similar wrapper.
No, it isn't, because it's a head wrapper in the way that we're imagining it here, right?
Oh, here, yeah.
And I think it has to be a head wrapper, doesn't it? Am I making sense? Yeah.
So what's the real difference between lazy and inactive? Because we know that inactive has a problem, which is that because it removes the attributes, and we have positive attributes like listable and negative attributes like hold first. By removing the negative attributes like hold first, it's actually activating things. And this is a problem with inactive. So I wonder whether this is the main difference between lazy and inactive.
Is what? That inactive basically just
I think the problem we have discussed other times is holding with inactive, that inactive lets things evaluate. And so it's activating things actually.
Yeah, that's weird.
But it removes other attributes like listable, which is good.
Mm-hmm. Well, your question is, could lazy, but you see, no, we want lazy of this to evaluate to some kind of,
Yeah, for constructors that do not need the hold attributes, this would work. Another approach would be to wrap lazy around the whole constructor call. So it's a lazy of range of infinity.
Yeah.
And the last option, though, is to have lazy range be the symbol, which honestly I think makes the most sense, because it's the same thing as like, we have nest list and we have nest tree. We don't have tree of nest of blah blah blah, right?
Well,
this is fundamentally going to be a different.
How many lazy objects do we need?
And we talked about this a bit last time. I was estimating a pretty low number, but then we came up with some other ones. I think it's still going to be,
Let's
in the
get
neighborhood
some
of
sense.
10-ish.
Let's get some sense of this, okay? So let's look at core language under lists.
But it's not
here.
even about the number of them. I mean, it's that, you know, if just because we had a bunch of constructors for trees doesn't mean we're just going to have a bunch of, you know, the normal list functions, but then we're going to have tree of nest of blah 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 does this. I mean, it's
Okay,
just
let's just make
a different
little
thing.
list. Okay, let's make a list of potentially lazy variants. Okay, we've got lazy range.
Then a constant array.
No, wait.
Yes.
We're going to go down this list.
Okay.
Roman. We're going to go down this list. We're not just going to jump. Okay, so lazy table, right? Lazy array. Lazy constant array. I mean, basically constant array.
I think lazy center array doesn't make much sense. Lazy subdivide.
You're right. Doesn't make
probably
any
doesn't
sense.
make much sense. It's just kind of range.
What about sparse array? Lazy sparse array.
I don't think that's coherent.
I
mean, that's a whole other data structure. All
right. Okay.
So you
Lazy
can imagine
tuples.
that you have a lazy list of array rules, and it's that's what lazy sparse array would be.
Okay, lazy tuples, lazy subsets, lazy subsequences, I think. Is that right? Or does lazy subsequences not make sense?
I don't actually know what subsequences does. I mean, I can guess what it does, but in which case I guess it probably would make sense, although there aren't that many subsequences.
No, I think it's much less necessary because you're not going to generate a large collection. Lazy permutations make sense. And lazy groupings make sense.
Mm-hmm. And
Does lazy outer
list.
make? Yes, lazy outer.
No, I was saying I don't think lazy outer makes a whole lot of sense. I mean, maybe, but well.
Well, if we enter linear algebra, this gets very slippery, and we get very close to inactive.
Right.
Okay, what about lazy fixed point list? Barely.
Yeah.
Nest while list, probably. Well, Christopher, your estimate of 10 is not far off.
Yeah, but I mean, we are pretty much, with few exceptions, this list on the left is just generated from the one on the right by prefixing lazy. So I wonder whether it's really worth the trouble, whether we shouldn't have a wrapper.
No. The whole point is, what we're asking is there a, just like with trees, just like with graphs, there are things which are almost the same, but we choose to have a limited number of functions because by doing this, we are defining there are certain functions that work, there are other functions that don't. Like we've said, lazy, center array doesn't make sense, so we don't provide it. Otherwise, if we did a wrapper, people would say lazy of center array, and then they'd be upset that it doesn't work. See what I'm saying?
Well, but
yes.
more philosophically, though, I think it's just like, for example, we have a nice analogy between associations and lists. And a lot of operations on lists also work on associations, and those are, that's how you do it. But we also have a lot of constructors for, associations that are analogous to constructors for lists, but where, we don't use like a headdress to specify them. I mean, we could have something like association of thread or association of map, and this corresponds to association thread and association map. But those are just different functions that produce a different data structure, and so we give them their own name.
Yes, I mean, generally using the data structure name in a constructor does make sense. So I'm not
okay. So then in this case,
not much opposed to it. I just thought that we could save some work,
no,
but
we can't.
Okay,
certainly
no
not
problem.
work. But I mean, so certainly not work because each of these has to be custom implemented anyway. Right. So, I mean, then each one of these would generate a lazy list. And the lazy list would, by default, as a Nix implementation, would display as a blob. It might have some kind of might have some kind of interactive behavior where you can explore more of it. I'm making sense. See, the thing that's worrying me is that we're going to need a lazy expression in the end. See what I'm saying?
That's why my initial suggestion was basically treat any symbol with hold as a lazy data structure.
But then the problem is we don't have operations.
Well,
I mean, if you just say it's a general expression, it's like, okay, then what's the API for this? What can you query from it? What are the set of operations? It's just so amorphous.
It's
Yeah.
like you can map over hold, right?
I mean, sure. I mean, there are operations like, I mean, if you assume that it's list-like, then sure, you can map over it. But again, you still have to make, I mean, just as we were talking about earlier with trees versus graphs versus arrays, whatever, you have to decide where you're sort of cauterizing it and where sort of the lazy edges are. And I think doing that with a general expression is very hard. I mean, unless you just say it's like the trees, it's lazy in the leaves or something like that. But
okay, so the advantage of a lazy list is we know the basic shape of the list. We know we don't know its elements necessarily or how big it is, but we know kind of what its shape is, what's overall, I don't know what you want to call it, it's not going to have any surprises, and that's where a graph is more complicated because it might loop back on itself and so on.
But tree is not, and any expression is a tree.
Right, but even our lazy trees, though, I mean, I guess we could have a tree that's doubly lazy in the sense that, like, even our trees, though, our trees are not lazy in the list of leaves. They're not lazy in width. They're only lazy in depth, if that makes sense. Or they're not lazy in length, I should say. They're only lazy in depth.
Yeah,
we could maybe have one that is dual lazy, where it's lazy both in the width and the length and the depth. But I don't even know. I mean, I guess we could have various tree sorts of operations that go on that, but I'm not even sure how useful that is.
When I first implemented treefold, that's exactly what it was. It was lazy in both the depth and it contained a lazy list of children, and we decided to wait before going down that road any further.
Right. Okay. So this
did it seem promising though, or did it have some horrible problem, or was it too early to say?
Kind of too early to say.
Okay. Could also have a lazy list of children at a given node, right? Which is a different concept.
Also, the idea was, basically with nest tree, that gives you the laziness in the depth. And the idea was if you wanted to have a lazy generator for the children, you would just, use nest list or whatever to generate the children.
Yeah, exactly.
Rather than having tree simultaneously doing both.
Yes, I think that's right. Right. So, I mean, lazy tree. I mean, when we have nest tree, for example, not nest tree, tree level, for instance. Okay, tree level on a lazy tree would specify how many levels and what the traversal order is, and then it would evaluate down to that point in the lazy tree. Right?
Yep. Wanted to make a point earlier too that I think the traversal order belongs in the function that consumes a lazy tree, not in the lazy tree itself.
I agree with you. Yeah. I mean, the lazy tree is just the infinite tree, basically, or however far the tree goes. So the constructor for a lazy tree would be what? Lazy nest. I'm forgetting all of our constructors. Lazy nest tree, right?
Yeah.
We could also have, it doesn't make sense, lazy random tree doesn't quite make sense except for random tree. I mean, if we say lazy Categorizing tree, does that make sense? So I'm saying if I say a Categorizing tree, an infinite binary tree, what's that?
I think so.
Yeah, because that's only lazy in the depth, isn't it?
Yeah. But I mean, is that the
well, complete Categorizing tree also. Complete Categorizing tree is the depth. Categorizing tree would be the number of nodes.
Right, but this function, I guess the thing you'd really want is just to say complete array tree, and then you just give it k, and the depth is infinity or something.
Yeah, exactly. Right. AKA infinite k-array tree.
Although actually, I maybe take it back a little bit, because it seems like, I mean, one of the things we've been talking about, like for example, the XML case, is that there is value in having lazy but finite stuff. Although we've been a little bit interchangeable with lazy versus infinite.
Yeah.
Yes, and you're right that
For the tree
infinite
project, we need not only lazy tree, but like the lazy, tree expression to a different kind of tree expression. And we have an internal function called expression transform that's eager, but it could have a lazy version.
I don't understand this. I'm sorry. Back up for a second.
So in trees, you can have expression tree and tree expression, right? So that leads to the idea of having a lazy expression tree composed with a lazy tree expression.
And what would that do?
That would,
so you're saying it will make transformation
between anything expression tree can understand, any other thing that expression tree can understand.
Well, like we could do that with map as well. You could take a Nick's lazy expression, right? If you had a lazy expression, you could imagine doing a map on a lazy expression of certain parts of the expression. I don't know whether this is useful. See what I'm saying? I mean, I think this might be what Nick was talking about here. Was it, Nick?
Well, yeah, pretty close. Yes. I'm pretty close on implementing that.
What's that?
I'm pretty close to implementing that, all of this. Right. It's not that far off from the lazy tree that they have. It's just maybe different in formatting.
Yeah, I understand. I mean, I think the thing that'd be really good if you were to implement is just get these things basically implemented. Returning a lazy list, which is just a blob. You know what I'm saying? And where you do normal of it, lazy list would have certain properties that you can extract. But if you say length and so on, many eager operations can be just done on it. It has up values for many kinds of operations, like length, for example. Does that make sense?
Yeah. Well, length will be problematic.
Why?
I know, because if you have a sub value for lazy list, cause some issues. There are other codes there. Because sometimes I want to actual, because some of the code that I use already uses length of the expression, right? And if it's a lazy list, it's called.
Okay. We have to solve the problem. I mean, so there are eager versions, like things like length of lazy list, that needs to just work.
Perhaps this means these objects are atomic.
Yeah, I think they probably are. I think they are atomic. I don't think we should. I don't think we should have anything where you can go in and take the seventh element, because lazy list sub 10 to the 5, 10 to the 4 or something. Whoops. Should just do that. It should just go in and figure out how to get the 10 to the 4th elements. Right? It shouldn't in any way
pretty much
dive
any
into lazy list data structure.
Any operations on list that can
obviously
be made work should just
obviously.
via up values, right?
Yes, obviously. Right. I mean, the thing that I wonder, I still come back to, should length of lazy list be a transfinite number? Or should it just be infinity?
I mean, it's always going to be countable. I mean, with at least the lazy list that we're talking about. There are other lazy lists that might be different, but the lazy list that we're talking about is always countable, isn't it?
Yes, but so it's, well, but like a
lazy
list of lazy lists is omega squared.
List.
What's that?
You don't know it's a lazy list of lazy lists. Maybe the first billion elements are lazy lists, and then after that they're not. I mean, there's also the fact that I think we talked about how length should just, because if you want length to work in the finite lazy list case, then you can't have it just return infinity immediately.
No,
So
it shouldn't.
it'll have to just run forever.
But I would assume that one property of all these objects is that they have a definite length, which might be infinite, but it's definite. It might even be symbolic.
Well, but I don't think you can do that, because, like, for example, if you do something like for example, suppose I consider the following lazy list. I say infinite range. I map prime over that, so I have now an infinite list of primes. Or I maybe implement some prime sieve or something like that with a select, and then I say or I say select prime infinite range comma prime cube, length of that. Knowing that that's infinite is non-trivial.
And if
insert
primes,
joke about zeta function or something, right?
Well, twin primes, you just can't do it. It doesn't know.
Right.
I mean, the question is, do these lazy lists have some optional meta information? Like, if we know the length, we could store it, and then it could say infinite. And if you have an infinite lazy list and you do a select on it, and then you ask for the length of that resulting lazy list, it could say indeterminate because it doesn't know.
Possibly, yes.
I guess so.
Like,
I feel like it's a little weird to have these sort of, it sometimes has a length and it sometimes doesn't.
Well, it just, we don't know. But I mean, if we don't know and I ask for the length, then I have to be prepared to wait until it has counted the elements. And
well, if you say range of infinity,
yes,
we should say the length of range of infinity is infinity.
Sure. Yeah, I mean, in many cases we can, but obviously once you start applying operations that transform a lazy list into other lazy lists, you may lose.
Right. So there's some operations that preserve the length of the list. Mapping something over the list preserves the length of the list. Selecting does not preserve the length of the list. Therefore, length can no longer be certain of what the length is.
Yes. And so the question is, do we just provide as much information as we have? If we know that a list is infinite, then we can say...
I kind of think probably yes, but we need to actually try it.
Otherwise, if we do that, and then it's just too easy to accidentally type length of some lazy list, and then a minute later you have to abort your computation. So there is a...
No, having length loop forever is stupid.
Yeah, I mean, so what do we
do?
Useful. Do we just say, if we don't know the length, then just give an
I'm sorry,
message?
actually, wait a minute. Wait.
But if I say lazy range of, and I ask to make a thing of length 10, and I ask for length of that, I mean, it's either going to return indeterminate, or it's going to also sometimes loop forever.
Guys, no, look, guys, look, there are cases where we know it's infinite, and it's trivially provable that it is infinite. And as we do operations on a lazy list, we should store in the metadata whether the operation that we did is a one-to-one operation, like map, for example. Okay, if it is, you can keep it as infinite. If it's a select, well, then there might be some theorem you could prove, or you might just give up and say we don't know the length.
Maybe. I just predict that two things. One, I predict that it's going to be... I predict it's going to be kind of, it's going to make it much more painful, and it's going to be a much heavier weight thing if every time you sort of implement a different operation on one of these, you kind of have to, at least for the primitives, you're going to have to, to include information, all sorts of meta information. For now, it's the length, but maybe in the future, it'll be something else too. And then the other thing, yeah,
go ahead. Sorry. Yeah.
No, go ahead.
Isn't it also the case that a typical program on lazy lists would never ask for the length? Why would it do so? I mean, that seems an operation that you just don't do on lazy lists.
No, that's not correct. If the list is, let's say you do a select of a lazy subsets, let's say you do a select of a lazy subsets with some function, and you expect that the answer is 1,000,000. But the subsets, there were 10 to the 20s, I don't know, let's say there were 10 to the 12 subsets that were generated, and you believe that the answer for that length thing will be 1,000,000. That's a perfectly reasonable thing to ask for. The computer runs overnight, enumerating each of those trillion, subsets, and then you've done this lazy select, so to speak, the select on the lazy object, and then you can count the results, and there are a million of them. Now, I admit that in that case, the results that you're getting are a non-lazy set of results. Otherwise, you don't know the answer.
Here's maybe a more programmery practical example would be something like I'm reading a big file and I'm reading it as some sort of lazy list.
Or lazy
you know
string.
the length or lazy string, right? You probably know the length. In a string, it's probably more complicated actually, because there are things like the way Unicode works and so on. But for a list, well, actually, I guess it depends on what the list is of. Maybe never mind. I was gonna say you might know the length of the file.
Yeah, you might from some system call that's sort of outside.
But if you just know the number of bytes, it doesn't. Unless you're importing it as a lazy list of bytes, you're probably not gonna know.
Well, I mean,
so
just
maybe
to
that's
be
not
clear,
a realistic example.
There is the possibility of, not that we necessarily want to do it, but there's also lazy byte array. Relevant for importing like that, where you couldn't know.
Yeah, I mean, because we already have so many. I mean,
byte array
I think
operations.
Because we already have because we have so many byte array operations. I mean, also because I think the whole point of byte arrays is that they're low level and fast, and I think
that's too weird.
The point of that. Yeah, fine.
I suspect lazy string is seriously interesting. That one I think is interesting because, it's one of these things where you could go examine the string. You could be streaming through some very complicated file looking for some particular thing. You could imagine doing a grep, basically.
Wouldn't that pretty much be the same as the lazy list of the characters of the string?
No, not in practice. Because, look, imagine you've got a terabyte-sized file, and you want to search for every element of every word that occurs just before rhinoceros. Okay,
that's a finite case. So I mean, what one question is, what string operations would be defined on an infinite string? So I mean, there's certainly lots of things that would be defined on finite strings.
Yeah, okay, I'll give you an example. The weather reports from random airports, they're going to keep coming forever, presumably.
Yeah, that's not a function. I mean, I'm asking like string cases. Is there usage of string cases that makes sense on an infinite string? Like we certainly have things like that. Like string cases would probably make a lot of sense on a very big, so you want it to be lazy, but still finite string.
Yes.
But I'm asking about the infinite case.
I admit that the only infinite case that I can think of is this one where there's a streaming data, and that streaming data has just keeps going forever.
But what function? I mean, this is not
no, I understand. I don't know how to return. The only function that I can imagine is first position of rhinoceros, and it keeps going until it finds the first rhinoceros.
Okay, sure. I'm not sure we have an existing string function for that, but yeah.
Well, operation that might on infinite strings. What do we do have that? I mean, in a sense, that string cases comma 1, I think.
Does string cases have a thing where you can tell it how many cases defined?
Pretty sure. Cases does.
Oh, you're right. It's third argument, the n.
Yeah,
sure.
Okay.
So I guess on the other usages, though, I guess it would just hope that it's finite.
Yeah.
And it'll probably run forever if it's infinite, if it doesn't know if it's infinite or finite.
Right. But I mean, it's just going to keep looking, right? It's going to keep looking for a rhinoceros, or it's going to keep looking for a yeti or something. If it doesn't find a yeti, it's just going to keep looking. Okay, we're not going to get too much further here today, but I do just want to set our. So I think we've got a pretty reasonable approach here to the lazy stuff, although I don't like the word lazy, but I think we should start implementing with that word in there. I think the next big thing is computation objects, of which our friend trace graph, I mean, again, we went through this last time, right? I hope we haven't forgotten those notes here. Where is the, wait a minute, where is that? Where are those notes? Notes, please, of.
If notes from last time, SW notes 01 were your notes from the last stream. You have it open.
Okay. Yeah, there may be some operations. I don't know what lazy splits is. I vaguely remember from last time. There may be a few things which are operations on lazy objects, which are new constructs beyond the ones we already know. Okay, this isn't what I was talking about. Maybe it's the one before this. What I was talking about is when we talk about, look, okay, a computation object. This is what I was talking about before. Remember, rules, function, evaluation. The constructor, right? Constructor has the version of, it's like, do you remember what I'm talking about? Nick, you remember what I'm talking about?
I mean, the same thing for the lazy objects.
No, not really. I mean, we've got the concept of, well, maybe yes. We've got iterate.
Well, if it's a constructor, maybe it's some kind of maybe a path.
We went through this before. Can we please find the notes from this? We went through this exact thing before, and this is what we need to actually go ahead and implement now. Right? We talked about how we can get it with rule application, we can get it with function application, and we can get it with down values. Am I making sense?
Oh yeah, I see.
Right? Those are the cases. And each one of those, we're basically making a
But isn't it a construction of a lazy object, not a computation object?
No, this is also a computation object. Okay, you're right. We could do this as a lazy object too, but we also want the computation object. So we want, just like you can say lazy nest list. Actually, we don't want lazy nest list. We want lazy nest. It's something like this, but that's not the actual right term. Lazy nest object f of a net. Okay, and that becomes a computation object or something. Maybe it's, for now, we call it lazy computation object. Am I making sense?
Yeah. I still understand how it is different from the just lazy object then. If you specify a function,
but because I'm telling you, because it contains, okay, the lazy object is the output. Okay, the output. It's the lazy list. It's the output. It's the result of running nest list or whatever it is, or nest or whatever. The output, not how you got there, just the output. Just like every other function in the system is just the output. You see what I'm saying?
Where it's like you return an initial lazy object which has evaluated none times, 0 times. This is the computation object, and then you evaluate it.
No, it's not. No, it's not. No, it's not. It's a generator. It's not got the. It's the difference between nest and nest list. Okay, nest just gives you the result, right? Nest list gives you a trace of how you got there. Am I making sense? So one of these things just gives you the result. The result happens to be a lazy object that contains a generator that when you poke at that lazy object, when you inspect the lazy object, it might have to go run the generator further.
Okay. So lazy object is just a part of a computation object. Right. At least
that is correct. Yes, it is the result. It is the, For example, a lazy object might be a slice of a computation object, or it might be the fixed point of the computation object. Does that make sense?
What is, hold on. What do you mean a slice of a lazy object?
No, a slice of a computation object. Computation object is the running computation, okay? It is a computation that can be continued, it can be run, you know, okay? And so the slice is something like this, right? That's a slice of a computation object.
Okay. It's just, there also can be a slice of a lazy object. It's like computation.
I know, but look, a lazy object
plus metadata.
The important point about a lazy object is it may not all have been computed yet. But if you said normal on it, it's just boom, it's all there, and it contains no history. You see what I'm saying?
Yeah.
Right? Whereas a computation object, which we have never had in the system before, right? The lazy object, we've had things a bit like it, like sparse array and things like that. Am I making sense? The only thing we've had that is even vaguely like a computation object is nest list or nest graph. Right? But they're not very adequate because they don't have event information. Nest graph only has state information. Am I making sense?
Yeah, sure. I understand. So, well, in practice, I would implement computation object, just some lazy object with metadata. You can continue a computation, you can store its history, take slices, and so on.
Yeah, exactly. There's nothing, but the whole point is that there is a conceptual difference between the lazy object, which is just the output, right? That where we happen not to have generated it all yet, but it is an output object. Okay, and then this, now in the computation object, we then have functions like find path, like now, you know, it's a different thing. In the lazy object, we have things like find the average value. Right? That could work across an infinite lazy object potentially. We could estimate that somehow. And I really think this is about right. Now, the difference, the thing that we've got in rule application, function application, down values is each one of those has a traversal order, which could be a single way traversal order. It's otherwise known as event selection function for the multi-way system. It could be a single way thing, or it could be a multi-way thing with a certain choice of sort of foliation. Does that make sense?
Sure, yeah. Selection function.
Right. But now the tricky thing about the foliations, in the case of rule application and down values, okay, the case of function application, all we have is potentially, okay, so look, if we say function application gives time-like extent and branch-like extent, because the function application, we're assuming that's the case where the function maps, you know, X to the list, you know, ABC. See what I'm saying?
Yeah.
Okay, so that's a branch-like extent, but there is no space-like extent here. In the case of rule application, for For the replace case, there is also just time-like and branch-like. For the replace all case, there is also space-like. Am I making sense?
Or we can also say for a function application that map all is also have a space-like extent.
Yes, if we used map all, or even map.
Map at position.
Yeah, map star star xxx would also have space-like. Okay, now there isn't a big distinction here in the case of function application between branch-like and rule-like. Because in the case I've just described there, that is in fact, that's also got rulial extent. Because they're different rules, right?
Well, I wouldn't really distinguish that.
I know.
But
Branch-like and
from
rule-like are the same in this case.
No, I mean, even for the rules, if you have just a multiple rules, I wouldn't distinguish it with some single rule that is just have a more complicated pattern on the left-hand side.
Possibly that's true. I don't know. What I think one might consider one branch-like, one rule-like. But anyway, I mean, so we've got rule application. So we've got these different cases, which are all where we need to be able to control. In each case, we've got to define what is the foliation that we're going to use. Well, maybe we don't have to define that when we're just defining the computation object. Maybe the foliation is in the eye of the observer, so to speak. Am I making sense?
Yeah.
And so then we want these three cases of creating computation objects in these three different ways. And let's not shoehorn them together because they're not going to fit. Do you see what I'm saying?
Yeah, so we can have lazy evaluate that produces a down.
It's not lazy evaluate. I don't think it's lazy evaluate. I think that's a mistake to call it that. I think it's
evaluation
well,
object. I don't know.
Yeah, I mean, I don't know. It's I mean, I don't know whether this is kind of like a.
Well, for now we can call them just lazy replace, lazy apply, lazy evaluate, and we know which is which.
Let's call it. It's not apply, it's lazy construct. It isn't even that. It's because it's got lists in it. Well, I mean, this should really be an object. We should say, because it's really different from a, you get what I'm saying? It's making the thing with the history, which is not the same meaning as lazy for a lazy list.
So this is the result of a function.
I know, but it shouldn't be called lazy apply then. It should be called something different.
Yeah, I know.
Okay, so it's something like lazy apply process or something. That's not the right name for it, but it's something which is a process, it's a representation of a process, not just the result. Am I making sense?
Yeah.
Okay, but I agree that so if we have these, then we need the functions that you've already started building, like find path, and so on. And then we also need Ian's trace graph. And we should have a version of trace graph for each of these cases. Am I making sense? Right, we built the one for evaluation. We need to build these other ones as well. Do you get what I'm saying?
Yeah, I get it, yeah.
Ian, do you get it?
That's not for me to do, though.
No, but it will be informed by what you have. And I want to make sure you understand what this is.
Yeah. I mean, trace graph is essentially a hierarchical thing. It's showing the nested evaluation chains, and things like replace all aren't necessarily going to have nested structure like that.
No. They are. It's going to be okay. You've got a different thing. You've got tree-like. In addition to the space-like recursion, you've got tree-like recursion into expressions. Okay, the graph that you're making should look like, up to the fact that it deals with sub-expressions on the expression tree, it is just like if all it dealt with was hypergraphs, okay, rather than expression trees, I believe it will be exactly like what we have in the physics project with space-like, time-like, branch-like edges. Am I making sense?
Yep.
So it's not, the trace graph is not strictly like a expression tree thing. It's a subsidiary evaluations. Like that also covers non-standard evaluation.
Sorry, say that again.
So the trace graph is not necessarily just about expression recursion. It's about an evaluation that requires subsidiary evaluations, which sometimes is just expression recursion, but not always.
I understand, because it has events that look in the events that happen there. An event could consume stuff. Yeah, that is expressions that came from non-standard places, I think. I mean, yeah, but I mean, in the case of function application, I believe that is a pure multi-way graph of the kind that we've always had. Do you agree? Nick, do you agree? Or other people here, do you agree?
Yeah, it's always, in all of those cases, just a multi-way graph.
In the case of function application, okay, so this here, the evaluation graph or the execution graph is just a multi-way graph. And again, it can have, you know, the variance of that, like a token event graph and so on, can be there too, right? In that case, the events are rather trivial. Every edge has an event on it. Am I correct?
Correct.
Okay. So in the case of rule application, it's not just an ordinary multi-way graph. It's just, this is in a sense a states multi-way graph. This is something beyond that, right?
Or in what exact sense? So, for example, rules can overlap.
Yeah, which means that it's a, look, as we said here, I know, we got to just start generating some of these things. The evaluation case is what Ian has already handled. No, he hasn't handled. He's handled the evaluation. Ian has the single way version of this. Am I making sense? The evaluation that shows spatial recursion and time-like recursion, but it doesn't show the multi-way stuff, right? Doesn't show the branchial edge, you know, branchial extent. Oh God, I've got to go. Sorry, guys. All right, we made some good progress here. Let's keep going on this. I mean, so Nick, if you can try and implement some of the things we've talked about here, and you know, does that make sense?
Yeah, sure.
Okay, and let's make sure we follow this. And when we add, if you want to add a Swiss Army knife, add it in a different place. Am I making sense? So we really make sure we have these functions are very clean and well defined. Okay. You can put the innards of a lazy list can be full of Swiss Army. I don't know whether the Roman can perhaps tell us more about the history of the Swiss Army knife and whether do they issue them to people in the Swiss Army?
Oh, yes, yes.
Do they have like particularly fancy ones? Or
No,
maybe
no.
it's
I mean,
classified.
those are very, very basic. I mean, they have to be practical and robust, and they don't need USB sticks and 10 different screwdrivers. I mean,
Fair enough. Yeah. And they don't have a horse hoof thing they always used to have. Thing for cleaning up horses' hooves or something. Maybe they lost that.
no, that must be a long time ago. I mean, there are no more horses in the Swiss
Army. Okay. All right. I gotta go. Thanks, guys, and to be continued.